Hi all, today we are going to discuss about parallel operation of transformers. So what is the need for parallel operation? Why should we go for the parallel operation? So when the power demand increases with time, because we know the loads will go on increasing in any area. So when the power is increased, if the limit crosses the capacity of your transformer, there are two options. Either you can replace the transformer with a higher capacity, but in that case you have to throw the existing transformer, which is very costly affair. Or second option is the power supply can be increased by adding one or more extra transformers in parallel, because it is a cheaper and easier way to do it. And there is one more advantage: in the instant of fault of one transformer, let us assume fault happens in some transformer such as like Bachholz relay is operated due to some internal fault, then the second transformer can maintain the supply, though maybe at the reduced level. At least some part of the power supply can be retained even if one transformer is disconnected. If entire area is supplied by a single transformer, entire area will be disconnected. That is a disadvantage. So the transformer can be switched on or off depending on the power demand, so that the losses can be decreased, because we know the transformer will be designed to operate, the distribution transformers are designed to operate between 70 to 80% of the full load. If it is operated around this load, so at this point the copper losses will be equal to the core losses, so overall the losses will be minimum. So if the transformer is operated less than this load or more than this load, then automatically the efficiency will fall down or the losses will increase. And we know that continuously the power on the load on the transformer will goes on changing according to the load that is required in a particular area. We can connect multiple transformers in either adding or removing the transformer, so thereby the overall efficiency can be improved. So now coming to the next one, the cost of the standby or spare unit is much less than two or more transformers are installed. So when you are installing more than two transformers, because always we have to maintain one spare transformer, because we don't know when problem will come to any one transformer. So the spare transformer capacity will be capacity of any one transformer. So if small transformers are used, the spare transformer capacity will be less, so automatically the cost will be less. Same thing is done for the case of generating stations. Multiple generators are used which are of a little bit of smaller size capacity, so that the spare capacity requirement will be less. So let us take a transformer. There is one transformer A, there is another transformer B, which you want to connect B in parallel with A. So in that, what is the condition for connecting? So when you connect the transformer B with A, let us see what is going to happen. So before connecting these two transformers, what we will do, one terminal will be directly connected like this, and second terminal will be connected through a voltmeter, and the switch will be open circuited. So now this voltmeter reading will be measured. If the voltmeter reading is showing as 0, the meaning of 0 means the potential difference between this point and this point, that means neutral or the secondary side point of this transformers is 0, or we can tell the potential difference between the two transformers is equal to 0. That means they are inducing the same value of the voltage. So when V is equal to 0, then you can close your switch. Let us assume if V is showing 2 times of your load voltage, it is showing 2 times of your load voltage, that means the polarity of the transformers that are connected are in opposite direction. They are connected in opposite direction. So that is what we can get from here. So let us represent that with the equivalent circuit. So this equivalent circuit, so this transformer I can represent by equivalent circuit EA, and this transformer is producing a voltage of EB, and the internal impedance that I can represent by REA plus XEA, let us take it as ZEA. Similarly, REB and XEB, so this I can write as ZEB. These two are connected like this, and this is connected to a load. Let us take the condition of a no load conditions. So you can see here these two transformers are connected in parallel. So this I can represent in this form. So this I can represent in this form. If EA is not equal to EB, or let us take for example EA is greater than EB, what is going to happen? For that I am representing that equivalent circuit, so that can be represented in this form. EA is in series with ZEA, EB is in series with ZEB, and they are connected to the same terminal, and there is a load voltage V. There is a voltage V. So now I can calculate, because these two, let us assume EA is greater than EB, that means let us try to apply the KVL in this loop. In this loop I am applying the KVL. So when you apply the KVL, as EA is greater than EB, so there will be a circulating current. Let us assume some current is passing. That current I am representing by IC. So because the IC is passing, the IC will pass like this. A circulating current or IC is passing. So if you apply the KVL in this loop, so the KVL will be, I am moving from minus to plus for EA. So this will become EA minus ZEA into IC minus, because as the current is passing, again here also polarity will be like this. Here the polarity will be like this because current is dropping there. Minus ZEB into IC, and you are going from plus to minus for EB. So this will become minus EB. This will be equal to 0. Or from this I can tell that IC will be equal to EA minus EB divided by ZEA plus ZEB. So this will be the current. So generally the value of the internal impedance is very less. So this value is very less. So even if the small change in EA minus EB is there, then your circulating currents will be very high. That means even if the small difference in the voltage is there, still the circulating currents will be very high in the case of the parallel operation of the transformers. And now calculating your load voltage, that load voltage I can calculate like this. Load voltage will be EA minus that circulating current IC is there, IC ZEA. So this will be equal to EB plus IC ZEB. So if you are taking for the case of ZEB, you can see here this is plus minus and this is plus minus. So if you can apply, start from here, reach this node. So both are adding to each other. This will be equal to your terminal voltage V. So this will be the consequence. So the essential requirement for the case of transformer, because I want to maintain my circulating currents as minimum, even if the small change is there, the circulating currents will be extremely high. So this circulating currents will be extremely high if your polarity is reversed. If the polarity is reversed, then they are in opposite direction. So this will become EA plus EA. Even the voltages are same, they will add to each other. So that's why the essential conditions for operation of the transformer is the first one, the polarity should be same. That polarity can be tested using the voltmeter, I have already explained to you. And the second condition is the value of EA should be equal to EB. That means the voltage ratios must be same. Voltage ratio means secondary voltage divided by primary voltage should be same for both the transformers. So now let us take the transformer under loading conditions. So essential conditions are satisfied. Essential condition means EA is equal to EB and the polarity should be same, that is compulsory, so that the circulating currents will be equal to 0. So that equivalent circuit I can represent like this. EA is the first transformer connected in series with ZEA and EB is connected in series with ZEB, that is connected to your load, and your load voltage is equal to V. So now as EA is equal to EB, so whatever is the voltage at this point, same voltage will be at this point also, because this is my reference point. So with respect to reference point, EA is equal to EB, both will be at same point, so I can combine these nodes together. So let us assume the total current supplied to the load is equal to I, and the contribution by each transformer will be IA because it depends on the value of ZEA, and the contribution by second transformer is IB, which depends on ZEB. So let us assume the voltage drop across this impedance will be small v and your terminal voltage will be equal to capital V. So here you can tell that the value of V will be equal to EA minus V, or this I can write as EB minus small v. This will be equal to capital V, or the terminal voltage. I hope up to here it is clear to you. So let us try to write the equations for the same. So I can write the equations. V is equal to EA minus IA ZEA, or this will be equal to EB minus IB ZEB. So as EA is equal to EB, so this I can write as IA ZEA will be equal to IB ZEB. Agree with me? So from this I can tell the value of IA will be equal to, we know IA is equal to I into other resistance by total resistance. You agree with me? So this will be I into other impedance. Other impedance will be ZEB divided by ZEA plus ZEB. Similarly, I can calculate my value of IB will be equal to I into ZEA divided by ZEA plus ZEB. You agree with me? So both sides I am multiplying with V for both these equations. So I am multiplying with V here, I am multiplying with V here. So V multiplied by IA. So V multiplied by IA will be the power that is supplied by the transformer A. So that I am representing with SA. This will be equal to V multiplied by I. This is V multiplied by I. Let us represent with the load power or load kVA, that is equal to S multiplied by ZEB divided by ZEA plus ZEB, and similar way this will be equal to power supplied by the second transformer will be equal to overall kVA multiplied by sorry, so ZEA plus ZEB. So this way how to calculate this one. So let us proceed further. From this I can calculate my value of SA. SA I can write as S into ZEB divided by ZEA plus ZEB. This is what I have derived. So similarly SB we got as this S multiplied by ZEA divided by ZEA plus ZEB. You are getting this one. So from this I can take the ratio of these two. So SA divided by SB. So this will be equal to ZEB divided by ZEA. This is what is obtained. So from this we can tell that the kVA supplied is inversely proportional to the respective impedance. From this I can extend further. So from this I can write SA multiplied by ZEA is equal to SB multiplied by ZEB. You agree with me? So both these things I am dividing with V square. Both these things I am dividing with V square, or from this I can write this of the form SA. So let us take this one, ZEA divided by V square divided by SA will be equal to ZEB divided by V square divided by SB. So this is nothing but the base impedance. The base impedance, if you are calculating, the base impedance will be V square divided by S. V square divided by S, that gives my impedance, because V square by P, because P is equal to V square by R, this you have seen. Similarly S is equal to V square divided by Z will be there. So let us take it as a base. This is the base voltage, this is the base power. So from this I can write my Z base value will be equal to V base square divided by S base. So this is we are going to discuss in per unit systems, in power systems. So this I can represent as the Z base, because we are taking what is taking SCA, we are taking as the base. Similarly here we are taking as SB as your base. So this gives ZEA per unit should be equal to ZEB per unit, which are referred to their own base values. They are not referred to common base, because here the base is taken as SCA, here it is base is taken as SB. So now we can conclude that the desirable conditions for parallel operation of the transformer is the value of the impedance value per phase value should be, per unit value should be equal for both the transformers. So that I am representing in the next page. So I can tell that this should be ZEA per unit should be equal to ZEB per unit. So what is the meaning of this? Per unit impedance referred to their own base must be same. Either this one should be there, or the impedances should be inversely proportional to their respective kVA rating. So in that cases, each transformer will be loaded according to their kVA rating. That is the basic thing that is required. So now let us proceed further. So let us take the first transformer. First transformer I can take REA. I am drawing the impedance triangle, and XEA is the reactance. So this becomes ZEA. So this becomes the angle subtended by the first transformer, that impedance angle of the first transformer. Similarly second transformer I can draw like this. This is having REB and this is XEB. So this will become equal to ZEB. So let us represent as phi B, impedance of the second transformer. Getting it? So let us take for example, if XEA divided by REA is not equal to XEB divided by REB. So in that case, we can tell the phi A will not be equal to phi B. You agree with me? So now, let us take for example, this XEA divided by REA is less than XEB divided by REB. So what is the meaning of this? The value of phi A is less than phi B. So in that case, what happens? Let us take for example, this is my current of the first transformer. This is the current of the second transformer. With respect to the voltage drop across the impedance, so let us assume the voltage drop across the impedance I am taking by small v. So this is the angle subtended by the first transformer, phi A, and this will be the angle subtended by the second transformer. So what is the phase angle between these two? Phi A minus phi B. So your total current will be the vector sum of these two currents. So this will be the vector sum of these two currents gives your overall current I. So let us take the case when phi A is equal to phi B. That means XEA by REA is equal to XEB by REB. So if you are taking your voltage like this, so this is my value of IA. So IB also in the same direction. So this will be my overall value of the current. So if the angle is equal to 0, you can get for the same magnitude of IA and AB. If the angle between them is 0, so I will be far greater than the case. Here the IA is less because it is a vector sum. Or we can conclude that if XEA by REA is equal to XEB by REB, the overall value of the current will be more for the same current carrying capacity of each transformer. Let us assume current carrying capacity of each transformer is IA and IB respectively. The current will be more when compared to both are having different ratios of XEA by XEB. Or we can tell the kVA rating of your transformer will decrease if the ratio of XEA by REA is not same as XEB by REB. This is what is our observation. So let us try to summarize it. So from this we can tell that XEA by REA should be equal to XEB by REB. So this is also a desirable condition. This is also a desirable condition. So let us try to summarize what we have seen today. So we have seen that the essential condition for the transformer is the transformers must have same voltage ratios and they should have the same polarity. So how we will test the polarity of the transformers? Let us take for example, I am taking one transformer is connected like this. So there is second transformer, primary is there, which is connected. Primaries are already connected. Now coming to the secondaries, let us assume this transformer is first one. There is second transformer. So this is my secondary side bus bar. So the first transformer is already in operation. So I am connected this one. This second transformer I want to make in operation. So what should I do? I have to connect to this through some voltmeter. Getting it? So across this there will be a switch. So this switch will be closed only if your voltmeter is showing the reading as 0. If voltmeter is not showing the value 0, that means there is a difference in the polarity or difference in the transformation ratios. So that should be observed. If your polarity is opposite, then this will show 2 times of your terminal voltage. If your polarities are same, it will show 0. This is the essential condition for the transformer. It cannot be avoided. And then coming to the desirable conditions are the leakage impedances in ohms must be inversely proportional to their respective kVA ratings, and the per unit leakage impedance or the transformer base referred to their own kVA rating must be same. That means if you are representing these impedances in per unit with refer to their own base kVA ratings, with their own base kVA rating they should be equal, or otherwise if they are represented in ohms, they should be inversely proportional to their kVA rating. If this is done like that, the transformer will be loaded appropriately. So next class I am going to take 1 to numericals. So there I will discuss about this parallel operation of the transformer. What will happen if these leakage impedances are different or the ratio of XEA by REA is not equal to 0. That means the difference between these two is not equal to 0. So the ratio of XEA by REA for both transformers should be same for both the transformers. So in that case, phi A will be equal to phi B. So kVA will be equal to kVA rating of transformer A plus kVA of B, simple arithmetic sum. So overall kVA rating of your transformer will increase. I hope that what are the essential and desirable conditions for parallel operation of transformer is clear to you. So next class I am going to solve 1-2 numericals to clarify these concepts completely. If you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you very much.